Yeah, my name is Wench, and my project is titled Measuring Magnetic Fields from Turbulence Anisotropy in Molecular Clouds. And this summer I worked with my advisor, Xiao Xu, at the Princeton site. So for an introduction, here we were focusing on molecular clouds, and interstellar molecular clouds are made of gas and dust and exist in the interstellar medium. They are often referred to as stellar nurseries, as star formation typically occurs here. And so for this specific project, the observational analysis discussed was for molecular cloud Orion A. And so our motivation for this project is to study magnetic fields and their impact on star formation. And over here on the right, we just have a nice image of Orion A. So now on to discuss the importance of magnetic fields in star formation. So magnetic fields impact star formation in a few different ways. First of all, they lower the star formation rate by opposing gravity. They also have an effect on the initial mass function that has been studied. They also interact with the environment of the molecular cloud, and they allow things such as outflows and jet production to occur, which can affect the system and the star formation there. And I won't play this video right now, but we have one of a large cluster forming if anyone wants to see later with the slides. Now so magnetic fields. There are some other detection methods for studying magnetic fields, which we can later compare our results to. And one of the popular ones is known as polarization. So what happens during polarization is that as light travels, it is absorbed by dust in the interstellar medium. And so when this happens, the dust grains are asymmetrical and they're also elongated. And so thermal emission occurs from these dust grains after the light is absorbed. And it is known that the magnetic field is perpendicular to the dust grain's thermal emission. So once we find the thermal emission, we detect it, we can then determine the magnetic field. Over here on the right, we have a nice little diagram of that, of our observer and then the light source. And then this absorption happening as the light travels. Now on to turbulence, which we will talk about a lot today. So turbulence is a multi-scale phenomenon. It is often described as sudden changes in motion of a fluid or a medium, changes in the pressure as well as the velocity. Usually these changes are very sudden and chaotic. So turbulence occurs everywhere, but specifically we'll be talking today about in the interstellar medium, as here's an image on the right of a supernova occurring in the interstellar medium. And here magnetohydrodynamic turbulence is discussed because we are dealing with electrical conducting fluids in the interstellar medium. And an important point something to point out is that magnetized turbulence is anisotropic. This means that its value is different depending on the direction in which it is measured. And now on to turbulent energy, which will relate to our project. So this diagram on the right depicts something known as the turbulent energy cascade, where we see if we measure something on a large scale, there is a high energy, but as we measure onto a smaller scale, the energy then dissipates. So over here, we have an energy injection at a large length scale. An example of that could be a supernova explosion occurring near a molecular cloud. And at a small length scale, the energy then dissipates. Now on to turbulence and magnetic fields and kind of their relationship. So studying anisotropic turbulence gives information on the magnetic field. Over this image on the left, we see these two rods as well as the two rods on the right. We can think of these different rods as magnetic field lines. So magnetic tension makes it very difficult to bend these magnetic fields. However, when there is perpendicular turbulent motion, these magnetic fields can mix, kind of if you imagine like your hands going up and down, we can mix these different fields and make them easier to identify and to study. Now on to something called the Alfvénic Mach Number. So the Alfvénic Mach Number, or MA, provides information on the strength of the magnetic field. So the Alfvénic Mach number is described as the injected turbulent velocity, VL, divided by the Alfvén speed, where VA is equal to B the magnetic field divided by 4 times pi times rho raised to the 1/2, where rho is our density, rho or P, and B is the magnetic field strength. So just to keep in mind, a small Alfvénic Mach number, which is around less than 1, is corresponding to a very strong magnetic field. Now onto our scientific goals and our process. So our process for this project was to develop a theoretical understanding of content, then to apply the theoretical understanding to observational analysis. Our goals for the project are to measure B, or magnetic field orientation, by studying turbulence anisotropy, measuring the magnetization or the strength of the field, then focus on different regions of the cloud included in active star forming regions. And we can see over here on the right, this is a intensity map where these kind of brighter areas are regions where we're going to focus on where star formation occurs. So to discuss these channel maps, so basically what these are is they are maps of Orion A at various channel velocities. For example, this one is at 8,500 meters per second. So this is a 2D map. We know the right ascension and the declination. However, there is an unknown third parameter, which is the distance. And just to note, the different regions on this map are not of the same distance, although we do know that overall Orion A is about 400 parsecs away from us. Now onto these velocity centroid equations. So on the next slide, you will see something called a velocity centroid map. And from that, we can derive the structure function of the velocity centroid. So the velocity centroid can be seen by the integral over here. Notice that it is different from plane velocity simply because it has a density component as well. And this dm value over here is described as the column density. And so to find the structure function, we take 2 points on our velocity centroid map. We take its velocity centroid, divide by its column density. Same thing with the second point, we subtract them and then square the value to get our structure function. And here's an example of what the velocity centroid map ends up looking like. It is pretty similar looking to the channel velocity map, except for here, we are mapping velocity centroid instead of the intensity. And onto our structure function plots. So plotted over here on the right is the structure function for velocity centroid as a function of separation, or the length scale. And so the structure function is able to tell us information on both intensity and velocity. And these 8 different colored lines correlate to different orientations that we are measuring the structure function along. And so the code that we work with is able to identify all pairs aligning with a certain angle, and then measures the structure function of all pairs along that angle. And here to kind of just go deeper into breaking down the plot. So here, this plot is able to prove that there is anisotropy, as the structure function varies with the orientation. If there was no anisotropy, these 8 lines would all be the same. And as can be seen here, it is known that the slope of the structure function can help define the turbulent fluctuation at these various length scales, as we have these R over here is our length scale. And just another something to notice is that the structure function measure perpendicular to the B field is generally larger than parallel to the field. Now on to quantifying anisotropy. So we want to quantify anisotropy to find the B field direction and magnetization. We are able to quantify anisotropy as it is the ratio of the highest amplitude structure function to the smallest amplitude structure function. If you're able to see on the slide before, they were both highlighted. And then once we find this ratio, we can use this degree of anisotropy to find the Alfvénic Mach number. An example here is being this image. Once we know the ratio, we can look for the corresponding MA number. Now onto our results. So the theoretical slope for our project was r raised to the 2/3, which can be seen by this dotted line. And so our result in the blue is pretty similar, although we do have some slight variations in slope. And our analysis was able to estimate the orientation of the magnetic field and produce the degree of anisotropy, which I will go over right now. So over here again, we have our velocity centroid map, and we have this one at 8,500 meters per second. So we were able to zoom on this little region, and we were able to identify the orientation of the magnetic field, which was around 26 degrees from the negative y-axis, so over in this direction. And we were able to calculate a degree of anisotropy of around 1.59. Now onto our plans for the future. So in the future for this project, we hope to repeat calculations for other regions of the cloud. We hope to create a magnetic field orientation map. We want to quantify anisotropy with the Alfvénic Mach number, create a map of the Alfvénic Mach number, which will tell us the magnetization of the medium, and further study the role of magnetic fields in star formation. So thank you, everyone. That was my presentation. Thank you for everyone in the NAC program for a great summer.
Hi, Autumn. That was a really nice presentation. Thank you so much for sharing your work with us. Very well laid out. This is a new area for me. I am not super familiar with turbulence and the role of magnetic fields in this. And so I just have a question about one of the things you said in the beginning of your talk. You said that the magnetic field can reduce star formation by opposing gravity. And you also mentioned that it can affect the initial mass function. Would you be able to share with me in a little bit more detail about how it can change the initial mass function and what that looks like?
Yeah, so I know kind of in speaking to my advisor over the summer that with the initial mass function, I know that we noticed it wasn't really like one way or the other. Like it wasn't maybe same with the star formation rate where we know that it slowed it down. So I feel like it wasn't like, we didn't know if it raised it or really lowered it, but rather we saw kind of just an effect in the studies. And I'm not like 100% sure, but I know my advisor has like a paper if you wanted me to send that to you that kind of discusses in more detail and has some figures, if that would be helpful.
Yeah, that would be great. That's really interesting. Okay, yeah, thanks.
Great talk, Autumn. Thank you. I was kind of going off Kristen's question. Is there like, what kind of relationship is there between the star formation rate being reduced and the strength of the magnetic fields? Is there like a direct relationship there? Is there, something that's very dependent on?
I think, yeah. So generally when we were able to look at kind of like a field map of like Orion A, there was definitely like variation in the different, like the different regions kind of varied a lot with the direction of the magnetic field. I believe it was opposed it more. I'm not positive. I believe it like opposed it more when it was kind of like we had like a kind of perpendicular motion almost to the direction. Kind of similar with just like the opposition effect, I believe, with the medium, if that kind of makes sense at all.
Yeah, that does. Thank you.
I'm not sure if this is a silly question, but in your intensity maps that you showed where it had the velocity, what is that with respect to the like 8,500?
Oh, the 8,500 meters per second. So I believe that was kind of the velocity was able to be measured just by kind of studying the turbulent motions in it, and I believe it was kind of just like an overall value, if that makes sense.
So like was there an image that corresponded to zero velocity?
I believe there was a range, which again I'm not sure, but I can find it again, like of the different ranges we were able to calculate. If you want to, I could also send that to you.
And then you said you had a video to share?
Yes, if you all want to see it. Here it is. Yeah, so there's no words, it's kind of just the dynamic of it.
Are those supposed to be stars?
Yeah, I think so.
Cute.
I actually have a question for you too. While this plays, Autumn, what was your favorite part of the internship or doing this project?
Ooh, doing this project, I really liked making all the figures, I think, because I think this project was really like, rather than just getting numbers, I was able to like actually see the like the intensity maps and the velocity centroid maps. I think that was probably the best part. Yeah.
Thank you for answering that. They were really good, really nice graphs. I feel like they were very high quality. I normally have
Thank
to
you.
so thank you so much for sharing with us.